Please help me welcome to the stage Ron Fedkiw.
Okay, so to get started, I should point out that my background's not really in computer science or machine learning, it's in mathematics. I started back at UCLA as a mathematician. In fact, I was so into mathematics that when I graduated with my PhD, my gift to my advisor was to write this book and make him first author. It's an applied math book. This will give some context to the things I'm going to talk about in this talk. So I went to Stanford, moved to computer science, and been a professor there for 18 years. More importantly, I picked up a consulting job very early on in my first year with Industrial Light and Magic. And you all know ILM because it's George Lucas's company from the first Star Wars, going back to the 70s. More recently, there were 3 new Star Wars that he did, and then he sold the company to Disney, and Disney's now doing their own set of 3. When I first got there, my expertise was in smoke, fire, explosions. Basically, the computational mathematics work that I had been doing at UCLA could be transferred immediately into special effects. They care about the Navier-Stokes equations, they care about F equals ma, they care about all the things applied mathematicians and mechanical engineers care about in making movies because they have to do these sorts of things. This was one of the very first things that I did, one of the first big things, which was, this is a small CG model of Los Angeles, and this is a nuclear blast that we set off in a CG simulation to blow up LA in Terminator 3. We also did the liquid Terminators for Terminator 3 with the same sort of tech, and that sort of research on Navier-Stokes equations accumulated with the Pirates of the Caribbean movies, as well as Poseidon and a few others. And Stanford Code and Stanford grad students actually worked to bring you the Maelstrom, if you remember that from Pirates. This led to an Academy Award in 2008 for fluid simulation. And the neat thing about this was the foreshadowing. If you look, this is Jessica Alba, who some of you know as the Invisible Woman from the Fantastic Four series, from the original one, not the new one. And 2008 was also the year we released Iron Man. I should have brought that jacket. That's one of my favorite keepsakes. I have the actual visual effects crew jacket from the original Iron Man. That was the beginning of the Marvel Universe. So that was the first film, for those of you movie buffs who know this. And we started at that point bringing comic books to the big screen with the new tech that we had. That led to a bunch of new research in rigid and deformable bodies, basically fracture, destruction. We did all the Marvel movies, Hulk, Smash, that sort of thing, and Transformers, you name it. We did a lot of work on those things. This is an example of the Starship Enterprise crashing into the Earth, destroying everything, and that led to the second Academy Award. So for context, basically, movies are getting easy. We can bring all this stuff to the real world. We are bringing comic books to the big screen. We can simulate all these extravagant things now in CG. But the reason I'm here today is to talk about what we can't do. This is sort of background for what we can, but I want to talk about what we can't do. What's hard is cloth. Cloth is very, very difficult still. This is some early work we did on cloth. We had some early success. That's episode 2, Yoda's robe. Those of you who remember, he had a lightsaber fight scene, and his robe was going everywhere in that movie. And, Dobby's rag, whatever you want to call it. So those are 2 things we did very early on in cloth. And we thought cloth was going to be easy. We even did full clothing in the Terminator movies in 2003. This is California's governor, ex-governor. So that was fun. I got to wear the jacket from the actual movie. It's big. Anybody who says Arnold's not strong, they're kidding themselves. I could barely wear the jacket myself, and I'm an ex-weightlifter too. Something else which is hard are faces. Faces are very difficult. My student Rachel Weinstein, this was her PhD thesis to do Davy Jones' tentacles. So we had some face work early on to do off-human type things, but to do more human things is hard. The way we do faces is we usually put motion capture markers on the face, track those markers and get some feel for what's going on, but that's nowhere near good enough. In fact, for all the movies these days, a rotoscope artist has to go into every single frame and outline the lips and the eyes and contours on the face in order for us to get a better feel for what's going on. When they show the breakaway shots, we always show the mocap markers, avatar, whatever it is. You see the markers and the cameras here, and we sort of sell that as how it works. We don't tell you about the thousands of hours that humans do by hand. Just like labeling data in the AI so-called sweatshops in China, we have animators doing this in our motion picture effects as well. So that brings me to the machine learning part of the talk, which is why I'm here. And in order to preempt that, I want to say procedural methods are what I've worked in up till now, up to about 3 years ago. And by procedural methods, I don't just mean things with F equals ma or Navier-Stokes. I don't just mean things where we understand the physics or the mechanics. I also mean things like with algorithms and recipes. Anytime you can write down some formula for doing something, I think of that as a procedural method. If you don't know the formula, that's what AI is for. That's what machine learning is for. That's what we're doing, is we're bringing in data to sort of meet the gap. Now, we want stuff to be as photoreal as possible for the movies, so we can't do pure data-driven stuff. It's just not going to work. The gap is too big. Whenever you see that, it looks okay, it looks promising, but it takes you out of the realism of the movie. So the idea here is to use the rules as much as possible. The third bullet up here is to use the procedural methods as far as you can, and then to switch to data-driven stuff for the rest of the way, when we don't know the rules or don't know the rules well enough. For example, suppose for an actor's face that I could actually figure out the constitutive models for the muscle and how it contracts, which we can't do because that would require doing experiments on live humans and testing muscle contractions. Suppose I could figure out how the fat behaves. Well, that you could do. You could pull the fat out and do some stuff with it, but very quickly after someone dies, rigor mortis, all this stuff sets in, you get different properties. You can't do that. Suppose for a shirt, I could, test the material properties. Well, you have to know all the warp and weft, all about stitching, whatever. But then I need to know about the body hair on the actual person, which you're not going to know. And for the actor, even if I knew about the muscles and the fat and how it behaved, for a particular actor like Brad Pitt, I'd need a CT scan to figure out his actual geometry. So there's a bunch of stuff I'm not going to know as well as I should. So 3 years ago, I made a sort of shift in careers to start grabbing data from AI, machine learning, whatever, and using it to augment these procedural methods. That was motivated, in fact, by John McCarthy. This, do I have a pointer on this? Let me see. No? Oh, I do, okay. So this is the computer science building at Stanford, and this is my office. This is where I've sat for 18 years, which is nice. I had a good view of the fountain. I could look at it every day and see how far the water had to go to be real. But sitting in the next office right here was John McCarthy. That's where he sat. Now, John passed away about a decade ago, but for about 10 years, I got to talk to John every single day. Every day, I'd walk outside my office, and he'd be like, oh, I wonder if AI could do this movie stuff. He thought it was really cool. And in fact, the one thing we always talked about collaborating on was stirring cream in coffee. Because, there's the way the cream mixes, there's some stuff we don't know about the physics. And John was thinking you could maybe film a bunch of coffee, learn about it, and mix those two things together. John, invented the word artificial intelligence in his NSF grant proposal, so he was a great person to sit next to. But that led to this whole data-driven methods thing, and I've already given you the basic idea. Step one, take the procedural methods as far as they can go. For things like water, smoke, fire, destruction, that's enough and you're done, you can make your movie. But step two is, if you can't get all the way there, use the procedural methods as much as possible. Do not abandon them and just take the data. It's a big jump to go from nothing to the answer. Use the procedural methods to get as close as you can get, treat that as a strong prior, and then use data to get the rest of the way there. I'll talk about two particular examples we've been doing just recently. The first one is faces. I've been working on faces for a long time. This is a graduate student from the early 2000s. He's now a professor in his own right at University of Wisconsin. Just recently got tenure there. And we covered him in plaster masks. He sat here for 8 hours under hot lights until it dried. And then we pulled out this latex and scanned it in and built this CG model of his face with 20 triangles for every pore. So we were collecting data a long time ago. I'm a big believer in data. It's hard to collect the data. In fact, I felt sorry for those bees until I remembered what I did to my graduate student. So we put muscles, we made a muscle model. We built this from MRI. We actually did MRI on him to build a muscle model. MRI wasn't that great in 0405, but we did the best we could to figure out where they were placed. We put a finite element mesh down for simulation. We worked with people in biomechanics to get the best possible models for everything. And we embedded these muscles in the finite element mesh and could flex them and move the tissue around. And we built very photorealistic models for rendering his face. That's a rendering of the triangle mesh there. And we failed miserably. Just complete failure. I spent $125,000 on a motion capture setup for this, and it just didn't work. It was very uncanny valley. Now, sure, it got a SIGGRAPH paper, helped me get tenure, so good, right? But as far as like tech, we never used it in movies. It just wasn't there yet. It wasn't there. We didn't have the data for it. So jump 10 years ahead to 2014-15. Another graduate student, he had a much easier job. He just took a scanner, went around Yoda, scanned the face in, put the muscles in, and we were off and running once again. But a lot easier these days to do this than back in the old days of the first Matrix movies. In fact, his name is Matthew Kong, and he worked on the muscle simulations for King Kong, which is sort of interesting, the name crossover. That was a 2017 movie, Skull Island, and we used the tech there, so we're finally getting the face tech with muscles into actual movies. This is a big success, but it's not a human face yet. It's a gorilla, and it looked pretty good for a gorilla. It wasn't really uncanny valley for a gorilla, but for a human, we have more to do. So this slide I'm going to spend a little bit of time on. This is a very important slide in the fact that the first bullet is Matthew's whole PhD thesis, and the next two bullets are a whole second paper on this stuff. But I'm condensing it into the one slide to give you an idea. So here's what we have. Here's how our system works, the tech for it. Right now for movies, if you want to do facial animation, an artist sits down on the screen and moves a bunch of sliders around. One slider might open the jaw, one might make a smile, a frown, and he has about 200 controls. He or she has about 200 controls in order to make facial shapes. Well, Matthew's thesis allows us to target those facial shapes with a finite element muscle simulation. That's what his thesis allowed us to do. Why is this important? Because in animators, they pull on all these levers, they make faces that look nothing like the right face. They're completely weird looking, it's just moving triangles around, and it looks bad. So if we target them with a muscle simulation, what we can do, the muscle simulation preserves volume, it stretches in anisotropic ways, it does a lot of different things. If we can target them with a muscle simulation, we can get shapes that are better. We can use muscles as a regularizer. So if you're into machine learning, AI, optimization, regularization is very important. So our muscle simulations help to regularize the blend shape system the artists do. And so the first bullet is what Matthew's thesis does. It allows us to take a blend shape an artist makes of, say, a smile, target it with a finite element muscle simulation, and get most of the way there, but not all the way there. What's left over are errors. And those errors are meaningful because the errors say that the artist is off model. He's doing something which is going to look wrong to the viewer, to the person watching the movie. In fact, even for computer vision, when we scan in faces, those scans have problems, like the nostrils will be too thin quite often, and this can help regularize them and fix the scan in data collection. So what we do is we take every blend shape in the system and we tweak it, smile, frown, whatever, all 200, and we target them with Matthew's system, and from that we build a muscle model under the hood. So we see where the muscles go. And instead of having a bunch of triangles in a smile shape, we have a bunch of muscle triangle surfaces in the smile shape. And we also check and see what the activations are for every muscle to see how much each one's flexing, how much tension there is. And so with that, we build this system you see down below, which is actually the artist's same system, tweaking all the parameters, but what the artist gets back is something like this instead of the actual outer face. If the outer face does really bad things, the muscles can't do them. It's regularized. The second step then is the second bullet. This is the new thing, to run a finite element code or simulation using these muscles to drive it, using what the artist intended to do in order to drive the tissue deformations. And from that, we have a system now where the artist pulls stuff up and down, and they get a face shape just like before, but instead of having it just be a bunch of triangles on the surface, now what we have is a bunch of triangles on the surface driven by underlying regularizing muscles. So there's like a delay, but we put the muscles and the regularization into the loop in order to make the stuff created by the artist more realistic, less in the uncanny valley. And nicely, we can differentiate the vertex positions with respect to the controls, so the way we put the muscles in, we still have differentiability in this. Then we take the output, say this, and we render it in a photorealistic way. Here's a different pose also rendered. So here's our actor. We get textures, we estimate lighting, we get some photorealistic style render for him based on the shapes. We use the renderer, the ray tracer. We use it in the lighting and everything with spherical harmonics in a way that is fully differentiable. So we need a fully differentiable renderer, which means if you take a pixel here and it has some color, you can differentiate it with respect to the vertex positions of the mesh, and you can differentiate those with respect to the parameters that drove the muscles, which means every pixel here with a color is controlled by an artist pulling a lever up and down. It's fully differentiable with those parameters. Then cue machine learning. Okay, there's all these face detectors out there. There's tons of them. I went to CVPR last summer and was wandering the poster aisles looking at 900 posters, and there were just tons and tons of papers on face detectors there in Utah. So I can take the real artist image or the CG one I made and feed them both through a face detector and spit out a bunch of key points for different spots on the face. Now, my rendering won't be as photoreal as this. I can work on procedural methods to make the render more real. I can work on procedural methods to make the face deformation and muscles more real. I can do all of that, but I'll probably never get to the point where this feels the same as this. It takes a long time to get there. So the network might spit out different sets of dots. Delete this and just look at the dots, for example. However, there's also tons of posters on fixing that. All you need to do is make a discriminator that tells you whether, given a set of dots, it came from a real image or my CG image. And once I have that, I can make a generator to fool the discriminator. And by running a GAN network on this, I can actually make the dots consistent between the two different sets of images, so when you see a set of dots, you don't know if they came from my CG render or the real image. Why is that important? Because then I can make a deep energy, which basically just takes the difference between the dots in the two images and treats those red line differences as a distance. And I take the sum of the squares of the distances and run standard optimization, classical optimization methods on that deep energy. I just take the Jacobian matrix and find out, based on the energy not being zero and these not being lined up, I find out how to tweak all those artist parameters to make them line up. So instead of having the artist go in and figure out how to match this, I can just solve an optimization problem to match it. Now, in this deep energy, these blue points are fixed. They don't move. These green points move around based on what the machine learning network did in this pipeline. And that depends on what the pixels look like, which depends on the vertex positions, which depends on the muscles, which depends on the underlying set of parameters. But I have a fully differentiable system that can go all the way through, whoops, I went one slide too far, and actually match up these two sets of markers and automatically predict now what the animator needs to do to match the face from the plate. Now, people built systems like this before and tried to drive them based on the parameters in general. And the one thing that we discovered here by accident, and this is the kind of nice part about science, you discover things by accident, was that if you look at blend shape parameters, they're a mess when you match something, but the muscle activations are really clean. The muscle activations turned out to be sparse and semantically meaningful. They corresponded to the muscles that would make a smile or frown or anything else, which means if I take a sequence of actor poses and I fit my model on top, this is a 3D model rendered on top of the actual actor in the plates, using this whole network that I just mentioned that we build up in that classical optimization. Down below, you see the muscle activations, and you see the blend shape parameters for each one of those frames. Notice when the mouth gets opened and he's really actuating some muscles hard to move the jaw, a bunch of muscle parameters like spike. But in the blend shapes, it's just going crazy every time because you're trying to match shapes in a non-semantic way. So this has great applications in a lot of robotics because you can actually look at people and figure out what they're doing. If a robot looks at this noise down here, there's not a lot you can say. It's just matching arbitrary shape to shape based on some arbitrary system. But if it's more semantically meaningful, then there's a lot more you can do with it. So I want to move on to cloth now for the last bit of the talk. One thing I want to mention before I get into cloth, which is something I've also worked on for a very long period of time, is that Amazon gave me one of these small grants that they give, gifts basically, to work on some of this cloth for e-commerce. And so I want to thank them for what I'm about to show. My whole reason for coming today is my appreciation for this, because when I started this work, we had no background in the learning part, and they funded one of these nice gifts in order to get me started on the learning aspect of the cloth. And so I'm extremely appreciative of that. So here's what we did for cloth, and I'm calling this a new paradigm shift in the way cloth is treated. Paradigm is one of the most overused words by academics that I can imagine. I have maybe 130, 40 papers, like 10s, 20, 30,000 citations or something, and I never use the word paradigm in anything, maybe once or twice, and this is the place I'm going to use it. So here I want to, I jumped too many slides. Here I want to make the sort of claim that it really is a big paradigm shift. It's going to completely change the way we do movies, e-commerce, everything. This is a big deal, and this is what I want to really stress here in this talk. So what we did was we took a cloth T-shirt, and we took the model for the T-shirt with vertex positions and triangles in the texture space. One important thing here with every step is it all goes on the graphics card. Whenever I go to CVPR, I talk to Jensen a little bit from NVIDIA, their CTO, and we always chat about new tech and this and that. He was a fan of my old Lighthouse simulations from pre-First Academy Award way back in the day, so I got to meet him back then, but we chat about this new stuff. One thing is being able to use everything on the graphics card makes it really fast. There's graphics and machine learning, both going to happen here, all in the graphics card. So this is going to be just fly based on the tech he's been making for both of those. So here's the way it works. We put the T-shirt in UV texture coordinates. So I'm going to use graphics words for this. And then we store displacements. So here I just take this and lie it down flat. We store displacements in texture and normal direction coordinates. So here I just created a random sine wave type thing for displacement and show this as a function. So each vertex here gets moved to some new location. It gets perturbed in U, V, and N. Okay? And then I can code that as colors on the vertices. Because this is just a three-dimensional space, RGB is a three-dimensional space, and so I don't actually have to worry about this. It's just colors on vertices. I call these cloth pixels. So from the cloth pixels, I'm going to make a cloth image. So I take these pixels, they're all on the vertices of triangles, and I use standard graphics rasterization to rasterize them to a background grid of pixels. And so what I have here now is an image, a two-dimensional image, which represents any cloth deformation you want. The way I'm going to work with this is I'm going to have an input, which are the animation parameters. You pick the joint angles of the model, the person, whatever it is, and they move around and change their pose, and the output's a 2D image. So it's completely set up for convolutional neural networks. It has all the spatial coherencies and everything, because I'm getting rid of this 3D deformation of cloth and encoding it instead into a 2D image, so I can leverage all of that stuff. And again, that's the strength of Jensen's stuff on the graphics card, is that it works really well for CNNs because it's so close to graphics already. Now, as a small caveat, you have to downsample these things, and you won't get the resolution you need for shirts. But this just works on patches, no problem, so you don't have to worry about downsampling and resolution. That problem is something you don't have to worry about. So the next big thing here is to make life easier for the network. It's hard for the network to predict from cloth lying on the floor in some pattern space to cloth moving around wrapped in my body, that whole function. It's a lot to actually predict. So I'm not going to make it so hard on the network. We know how to skin bodies in graphics quite well. Skinning is also on the graphics card. So if I have like joint parameters moving around, I can skin my outer surface. I can do this black body, no problem. And so what I do is I take the cloth pixels and I embed them on the body. I barycentrically embed them in the triangles of the body. So as the body changes pose, they move with it. What that means is if my t-shirt was skin tight and just followed these two things, the offsets I would need would be 0, and the machine learning network learns a function which is 0 everywhere. But if the cloth is dangling, it needs to learn offsets from here to the shirt. But to get the identity of the person, doesn't have to be in the network. We'll get that from skinning. As the person moves around and deforms their body, that also doesn't be in the network. We get that from skinning. We only need the displacements from that in the network, which makes it easy for the network to learn. So here's just an example on top of what I had in the last slide. I just repeated this. There are my pixels embedded in the body, moving along with the body as it's skinned. Here's that sine wave I showed you before, and the sine wave just gives offsets on this. As the body moves around, the sine wave shirt moves around with it. That's just the front half of the t-shirt. But this is a constant function. Nothing's changing. I'm just moving the body, and the shirt moves and moves the body because the underlying cloth pixels move as I move the body. So for training data, and here's where I need a lot of help. Here's where a lot of companies who can scan in cloth and this sort of thing are useful. There's a company, Body Labs, run by Michael Black, which was acquired by Amazon last year. They can scan cloth. You can also do simulations. But the idea is I need shapes of cloth. And from those shapes of cloth, I want to record the offsets from the cloth with some sort of correspondences to the cloth pixels. Those offsets are just distances from these points to the corresponding points in the actual shirt, and then turn them into colors and put them into my cloth image. And so my training data is a scan in a bunch of cloth, and then use the correspondences to make a bunch of images. Given a pose that you're in, I simply train from pose to image, and that's how I collect my data. That's my data collection framework. Here's what the results look like. So these are actual poses input. The ground truth is on top, which the network didn't know. This is generalization error, basically. And so my predictions are in the second row, and you can see that even though we just put this together in the last 4 or 5 weeks, it's not so bad for predictions. We can probably do a lot better than networks. This doesn't even use the cloth patches. These are all downsampled already. On the bottom, we show the actual errors, color-coded. Red's higher error, and blue is lower. This is the biggest accidental result of the whole thing. So I made this body so that I wouldn't need to learn that in the network. But suppose I got it wrong by a little bit. In the center is the actual body we use for the experiments. There's the actual cloth from that pose. There's a cloth image that corresponds to the offsets from here to here. Okay? Suppose I guessed the body was too fat and I trained the network on the fatter body. Or too thin and trained it on a thinner body. That just means the offsets will be different. So the cloth images just look a little different. The function's a little different. I can still train the same network to get back the same shapes, even on a fat body. Meaning, this body was so fat that the t-shirt is actually inside the body. But I can still predict it inside the body in the proper place, just like it was here. Why does this matter? Because if you have a company that's going to do e-commerce cloth and fitting, you are not going to get people in Iowa to scan themselves in naked. Not going to happen. You're going to get some people in Silicon Valley, some millennials, sure, it's really cool, this tech works, great, fine, but your market's going to be tiny, right? You can't ask customers to show you how terrible they look, right? No one's going to want to do that. And so that's the idea here is if you know what their shirt does, you can use any of these models underneath to drive the cloth pixels. So if you guess they're a little fatter or thinner than they actually are, it doesn't matter. I can train my network to fix that. And that's the big beauty of this, is you no longer need to worry about the technologies that scan in humans. You can actually have a person go into a room with a bunch of cameras, move around with a t-shirt, and you know the size of that shirt. You can pick a body model which you think is close to give the network a break, and you can train a network for that person and that shirt such that it doesn't actually need to know their unclothed shape, even though you're using one under the hood, which is an assumption. That allows you then to see what other shirts and other garments would look like on that same person without ever knowing their unclothed shape. And to me, that's the big breakthrough here. That's why it's a paradigm shift, because everyone's been worried about how they're going to get these unclosed shapes, how they're going to scan them in. Everyone's been worried about how they're going to do the simulations or the fitting of the cloth and the shirts, or the cloth and the bodies. And in the end, you don't need to know this stuff. You just don't need to know it. You can train a network, use the data to fill that hole for you. It sounds a lot like what John McCarthy told me about everything. He always said, oh, you don't know that? What don't you know? We'll fill it in with data. So also, body skinning is not perfect. There's errors in body skinning. So if I get you scanning a neutral pose, when you move and bend around, the point is your body changes shape a lot. And the more layers of fat or rolls or whatever you have, or muscle, the more your body shape changes a lot. So if you scan a person in a neutral pose, great. You might see how a shirt fits when they're standing like this. But if they bend over and do things, you won't know how it fits. That's all going to be wrong. You need to scan them in a whole bunch of poses. And the skinning allows us to sort of approximate other poses. But even if the poses are wrong in the approximator, our network can train through them. So the point is that doesn't matter either. You don't need that either. And so one of the big papers from CVPR last year that was doing this sort of thing said that, the hardest thing for them was neckties, so we just threw a necktie in for fun, and that worked just fine too. So it's got great versatility and the things you can do. Currently, we're just chopping up clothes and stuff, scanning them in, and building models and trying new stuff. But that's one of the places we could use collaboration. We need to collect a lot of data now. And we're not really a data collection lab, we're more of an algorithms lab. So this is sort of a reaching out to people if you have ways of collecting data. I hit my limit on time, so one last thing I want to mention. Typically, I do a 1-hour talk, so I'd have one more topic. I won't get to this topic today, but I just want to mention something else where machine learning can play a big role, where algorithms don't work, is in scanning technologies for the world. We put cameras on drones and fly them around trees, like good trees, Northern California trees, right? And we try to scan in the tree, and it just doesn't work at all. Here's some drone pass and the scree. These methods just don't work for something as complex. We want to build articulated rigid bodies for these trees so dinosaurs can interact with them, right? That's our goal here. And so we started using machine learning in these sorts of problems too. And it's a topic for another day. I always close my talk with a cup of coffee these days, thinking of John. Because 3 years ago, I went into this data-driven stuff to augment the procedural stuff I've been doing for movies, and it's really changed my life, and I have a lot of appreciation for John. I just can't thank him. And that's the end. Thanks.